My name is Professor Rob Hillman, and in this short presentation I'm going to talk about some of the ways in which chemistry at surfaces makes important contributions to forensic science. A significant amount of effort in a criminal investigation is expended on the location and identification of trace materials, marks and impressions on surfaces. And this is a consequence of the fact that direct physical contact between an item and a source results in the transfer of material between them. This idea is attributed to Edmund Locard, who encapsulated this in the phrase, "every contact leaves a trace." So we'll spend a considerable amount of time talking about the analysis of material on surfaces, and in particular, the imaging of that material on a surface when we look at a finger mark. And the relative importance of this is that fingerprints are unique identifiers of an individual. There are three types of fingerprint. The first is a visible one, in which there is a coloured substance transferred between the surface and the fingertip. An obvious example is the transfer of blood in a crime of violence. The second type is a plastic fingerprint, and this occurs when the finger is pressed into a soft material, so it leaves a three-dimensional negative imprint in that material. An example here would be the putty in a window frame when it's touched during the course of a burglary. The third type is a latent finger mark, and by definition this is a mark that is not visible to the naked eye. The mark is there, although we can't see it, and it results from colourless secretions that come from pores on the skin ridges on your fingertip being transferred onto the surface. And these secretions will be a complex mixture of water and organic and inorganic substances. And the role of the chemist here is to either carry out chemistry that makes this residue visible, or that makes the background on which it sits visible. So we'll get either a positive or a negative image. There are three types of fingerprint patterns. The most common is a loop, and then a whirl, and the least common is an arch. And I think the names are self-explanatory. And these are what we refer to as first level detail. Now, of course, with just three pattern types, that's not sufficient to identify an individual. So we now have to look in greater detail, so-called second level detail, for some of the finer features within the fingerprint. And here you can see some examples. And the first two are a so-called ridge ending, when the ridge abruptly stops, and a bifurcation when it splits into two. And you can see other examples there as well. The little white dots along those ridges represent the pores through which these secretions that comprise the residue are exuded. This is actually a finer level of detail referred to as third level detail, and this is not part of the identification process in general. So second level detail is where our interest primarily lies. So let's have a look now at some examples of how we can visualize these marks. And the first example I have here is where we wish to visualize a latent mark that's on a reactive metal surface. And the reactive metal in this case is copper. And if you recall your knowledge of the electrochemical series, you'll remember that silver ions, silver +1, are sufficiently powerful oxidizing agents that they will oxidize copper metal, copper 0, to copper ions, and then the copper ions will dissolve into solution. As that happens, the silver is reduced to silver naught, that's elemental silver metal, and it deposits on the surface. So you can see on the right-hand side in the little cartoon, we have silver deposited on the copper. Now the key point here is that the residue left by the finger acts as a mask or a template, if you prefer, on the surface, and the reaction does not occur there. So we only get deposition on the bare metal surface. So in other words, we get a negative image of the finger mark. Let's see how that works in practice. And we're going to look at some different copper-containing materials, and we'll start with copper itself. And you can see here that on this copper plate, and the copper color is at the top, where the plate has been dipped into the reagent containing the silver ions, the silver and the copper have reacted, and now you can see that the latent mark is revealed. This might be of relevance for example, on a piece of copper piping, because copper is a metal that's frequently involved in metal theft. It also turns out that this will work on alloys of copper, and brass is the obvious example here. And here you can see that a brass plate with a latent mark on it has been visualized. The forensic relevance of this is for brass bullet casings. Another example of an alloy involving copper is bronze, and here you can see that we've been able to visualize the latent mark. Now, in each of these examples, you can see the first level detail, and if you look closely, you can see some elements of second level detail. If we use a microscope, we can zoom in and we can see elements also of the third level detail. So you can see here we get very detailed images of a finger mark that would enable us to identify the individual. That works well for reactive metal surfaces. In the case of a metal surface that's not reactive, and an example here would be stainless steel, we have to adopt a slightly different approach. Now, because the metal will not dissolve, we have to drive the deposition process in a different way. And in this example, we're going to do it with an electric current. So if we imagine here is our piece of stainless steel, viewed side on, and we're going to deposit our fingerprint. And here you can see all the cross sections of all the little ridges. And then we're going to immerse this in a solution of a monomer, not to scale, of course. Here are the monomer molecules. And as we pass the current, we're going to oxidize them, polymerize them, and we'll turn our colorless monomer into a colored polymer. In the examples that I'm going to show you, one of the frequent molecules that we use is aniline, which is colorless or strictly absorbs in the UV. And when it's polymerized to polyaniline, this long conjugated molecule is now colored. And in fact, its color depends on the voltage that we apply. So here are a couple of examples. The top left, you can see a piece of stainless steel on which a latent mark is deposited. And then we've deposited a conducting polymer in all of the spaces where the bare metal is revealed. And if we look inside the red square, we can see, if we look carefully, a bifurcation. And in the central image, we can see this more clearly in the magnified image. And in fact, you can even see the third level detail of the pores there. This would be relevant, for example, to stainless steel that was part of a knife in a crime of violence. And on the right-hand side, you can see the stainless steel handle has the finger marks on it. Another example, now going back to theft, metal theft, is lead, and lead is frequently used as a roofing material on old buildings and regrettably is commonly stolen with the resulting damage to the buildings. Since we recognize that these polymers are colored, it's interesting to see if we can learn a little more about the film and the image from more detailed examination of the spectrum. And a simple way in which we can do this involves so-called RGB, or red, green, blue images. And you may be aware that many display devices, so perhaps a television, a mobile phone, when we see a colored image, it's in fact a superposition of a red image, a green image, and a blue image. And in these examples here, where we've used a sulfur-containing molecule, thiophene, and a nitrogen-containing molecule, pyrrole, and polymerized them, we can see that if we look at the red, the green, and the blue images, so that's A, B, C in each case, the images look a little different. In some cases, some areas are underdeveloped, some are overdeveloped, and some are just right. And by more detailed analysis of this, we can get perfect optimization of the image that's left on the surface. And of course, if we've done this with a mobile phone, we can readily transmit the image back to the analyst. Finally, I have another example of metal deposition, but now not on a metal, but on paper. And of course, the interest here for forensic science is that paper is involved in all sorts of documents. This might be contracts, wills, deeds of ownership, ransom letters, blackmail letters, and of course, paper currency. In this instance, we're going to reduce the silver ions to silver metal using an iron redox reagent. And again, if you remember your electrochemical series, you'll know that iron 2 can reduce silver plus to silver metal, so we can drive this reaction here, and we'll create small particles of silver in the solution, so-called colloidal particles. These will then adsorb on the fingerprint residue. So here's an example of a latent mark that was left on a piece of white copy paper, as you might use in your printer, and then it's developed with this physical developer. This magnification, the lines appear continuous, but let's progressively magnify the image. So let's look at first the red square, and we can see that the lines in fact aren't continuous. Let's go a little further, and we can see that the lines, the ridges, are made up of a sequence of very small dots, and those are the silver particles. In fact, it looks a little bit like a grainy, old-fashioned black and white photograph. And if we zoom in even further, we can see here are the individual particles. And the role of the chemist here is to be able to control the rate of the redox reaction, the size of the particles, and the ease and selectivity with which they adhere to the fingerprint residue to give us that nice sharp image. So let's just recap and think a little bit ahead too about the sort of things you might learn in a chemistry course that would feed into all of these and many other forensic science techniques. You'd learn about energy levels and the way in which that influences the colour of a molecule. You'd learn about the energetics of redox reactions, so we'd learn which reactions will proceed in which direction, and perhaps we'd also learn something about the rate as well. We'd learn about the dissolution of metals, so corrosion in an electrochemical process. We'd also see something about small particles in solution, so-called colloids. And these are materials that are, if you like, in the grey zone between very small entities, ions and single molecules in the solution, and large aggregates that we would have in the suspension. So colloids are on the order of micron size, so close to the same size as the wavelength of light. We also, if you remember, in the early part of the presentation, talked about the analysis of surfaces, and that may be their chemical composition, or it may be the surface topography. So a great deal about surface imaging in various respects. And I hope you'd be keen to learn a little bit about all of these things and the way in which they can help forensic science.